As we traverse the bustling cityscape, we witness a familiar sight: charging stations overwhelmed. Yet that isn't the only problem. The electricity grid is also pushed to its limits. As the demand for electric vehicles surges, the infrastructure lags, creating bottlenecks. Yet, what if the solution was within our reach? Imagine a smart charging network that directs vehicles to the closest, cheapest stations, reducing wait times and congestion while supporting a sustainable energy grid. We're breaking through electric mobility barriers, turning charging into a seamless process. Join us in revolutionizing energy access and advancing towards a future of limitless travel. Ladies and gentlemen, esteemed colleagues and visionary students, greetings. My name is Byung, a rising senior in the Elmore Family School of Electrical and Computer Engineering at Purdue University. Today, it is my distinct honor to introduce our groundbreaking project for the 2024 Curiosity Cup Challenge, a showcase of innovation aimed at revolutionizing electric vehicle charging infrastructure. Our project represents a joint endeavor among intellectual minds from diverse academic disciplines under Team ORSOL. Together, we are exploring new frontiers in sustainable transportation and infrastructure development, leveraging unorthodox data sources and cutting-edge analytics. Before we get to the crux of our presentation, let us first acquaint ourselves with the members who have made this project possible. Guiding our team is Professor Sivaranjani Siddharaman from Purdue University's School of Industrial Engineering, with their research focusing on power and energy systems and intelligent transportation networks. Her mentorship has been pivotal in shaping the direction of our research. Stepping into the role of project leader, I've been deeply engaged in dissecting the problem context of our project and envisioning our trajectory ahead. I'll guide you through the pressing gaps, and to conclude, I'll discuss our findings' impact on sustainable electric mobility and the exciting future developments. Jared, our data processing expert, will walk you through our project's analytics. His talk will cover our data collection, processing tactics, and how we've distilled complex data into a clear narrative underlining our results. Next, we have Jay, where he will detail the methodologies behind our predictive models. He will explain how we developed innovative techniques and their effectiveness in forecasting EV charging demands. Lastly, Ethan will present our research findings, where he will cover key insights and their implications for EV charging infrastructure impact. Without further ado, let us delve into the heart of the issue. We embark on our exploration by probing the increasingly pressing issue, the imbalance between the swift uptick in electric vehicle usage and the sluggish expansion of charging stations. Here we lay the foundation of our study, pinpointing the challenges our forward-thinking solutions aim to tackle. Diving deeper, we confront three pivotal challenges. First, the infrastructure lag, where the growth of EVs outstrips the charging station installations, creating a critical supply-demand mismatch. Our second hurdle is the complexity in charging optimization. Beyond mere numbers, the strategic placement and efficient grid and integration of stations are crucial. Lastly, and most importantly, we grapple with a data gap in demand forecasting. The lack of granular, public data on how, when, and where EV charging stations are used is a critical gap. Without detailed usage patterns, forecasting models struggle, as they typically rely on historical data that isn't always available. So what is our innovative solution to overcome this data gap in demand forecasting? We harness traffic flow data to mirror the behavior patterns of EV users, capturing when and where they are most likely to need charging stations. By analyzing the trends and volumes in traffic movements, we can predict peak demand times and locations for EV charging, enabling a strategic deployment of charging infrastructure that aligns with actual usage patterns. This method not only addresses the forecasting challenge, but also ensures that the expansion of charging facilities is both data-driven and optimized for future needs. Now, I'll hand it over to Jared, who will elaborate on the data and processing segment.
Thank you, Wooky, for the overview of our project's problem context and objectives. As we transition into the data and processing segment, allow me to explain the meticulous steps we have embarked upon. ensuring the management of our data within the SAS platform. Our journey through data processing is defined into 7 critical steps, each essential for the integrity and success of our data management strategy. Our initial phase began with the imperative task of assembling a real-world dataset tailored to our specifications, crucial for the development of our forecasting model. The California Department of Transportation Performance Measurement System, known as Caltrans-PEMS, played an instrumental role in this attempt. Our team crafted a crawler script enabling the automated download of suitable files directly from their database. Each acquired Excel file represented a day's traffic data, spanning a comprehensive period from January 1st, 2018 to December 31st, 2019. This led to the acquisition of 720 distinct files. As depicted in the provided example, the datasets encapsulated various metrics, including post-mile range, vehicle detection system numbers, ramp types, and hourly traffic measurements. To streamline data management within the SAS platform, we merged these datasets into a singular comprehensive file. This strategic consolidation facilitated more efficient data manipulation and analysis. In the pursuit of numerical purity within our dataset, we encountered the presence of the letter R within the post-mile range column. Determined to preserve the integrity of our numerical data, we elected to excise all instances of this alphabetical character from the column. Furthermore, our analysis took into consideration the geographical span of existing EV charging stations, selecting a focused range between 32.5 and 36.33 for our project. Upon inspecting the original dataset, we identified discrepancies and missing data points across various ramp types. To enforce the reliability of our forecasting model, our choice approach utilizing mainline data, distinguished by its completeness and the absence of missing entries. Subsequently, we extracted the requisite information, transposing it into a format conducive to SAS Via's analytical capabilities. This transformation was critical in preparing our data for the sophisticated modeling processes that lie ahead. With the data file seamlessly integrated into SAS Via, we stand on the cusp of advancing to the next phase of our project. It is with great anticipation that we now transition to Jay, who will illuminate the core methodologies underpinning our forecasting model.
Thank you, Jared. Now, let's talk about the methodology. Building on Jared's introduction, we've uploaded our process data to SAS Forecast Studio, setting the stage for our comprehensive analysis on EV charging demand. In our SAS forecasting model, we've selected a diverse array of predictive models: the ARIMA X, the ESM, the UCM, complemented by stacked, seasonal, and panel models. SAS Forecasting Studio rigorously assesses each model by evaluating statistical measures such as WMAE and WMAPE. The model demonstrating the lowest error rates is selected as the superior forecasting method, ensuring the highest precision and traffic prediction. In this phase, the SAS Forecasting Studio delivers practical outputs from our champion model, harnessing historical data to offer clear prediction of future traffic patterns. This forecast captures the behavior and trend over time, forming a reliable basis for anticipating peak usage periods. With these insights, we can devise strategies including optimization techniques for future work aimed at balancing the load on the electricity grid, easing congestion, and improving convenience for EV users. Having captured the traffic flow behavior through our chosen model, we now approach a pivotal aspect of our analysis: the number of electric vehicles exiting the highway that need to charge. This output is derived from a 3-step process involving sequential equations that will later on be explained more in depth. And this brings us to the full view of our framework. This framework acts as our compass, leading us from the granular specific of raw data to the wide-reaching scope of our predictive outcomes. Uniquely, we leverage traffic flow data, an approach not commonly employed in this context, to navigate the complexities of forecasting EV charging station demands. This innovative use of traffic data underscores our pioneering method, setting us apart in our quest for actionable insights and solutions. Here, we present our three-step analytical approach to discerning post-exit EV charging needs. Given the restrictions like the California Consumer Privacy Act and the California Privacy Right Act, we are unable to directly access individual EV charging station data. We address this by harnessing traffic flow data to predict the number of electric vehicles exiting the highway and likely needing charging. However, we face a challenge. The data we need to identify which vehicle will require charging after leaving the highway isn't directly available. To bridge this gap, we employ a three-step process involving a set of equations. These equations are designed to calculate the ratio of EVs on the highway, the ratio of vehicles exceeding the highway, and the count of EV exceeding highway needing to charge, respectively. Firstly, we focus on the equation 1, the ratio of EV on highway. Our objective is to quantify the presence of electric vehicle on the segment of the I-210 corridor that we are investigating. This ratio is calculated by dividing the total number of EV registration in California by the total vehicle registration within the state. We draw from the Department of Energy comprehensive data to ensure accuracy. Secondly, we transition to equation 2, which quantifies the vehicle exiting the highway. By taking the difference in vehicle count between the first and the last sensors and dividing it by the total number of vehicles passing the first sensor, we obtain the detailed exit ratio. This calculation is refined further to factor in vehicles exiting at intermediate points, therefore sharpening our assessment of exit patterns. Lastly, building on our previous findings, equation 3 allows us to estimate the number of electric vehicles that will likely require charging after exiting the highway. Utilizing the numerical values obtained from equations 1 and 2, we'll apply these insights to derive a pivotal figure by multiplying the total traffic count by the previously established ratios, the proportion of EVs on the highway and the rate of vehicles exiting. We are arriving at the final count of EVs exiting the highway in need of a charge. This figure is crucial in capturing the pattern and trend beyond the raw traffic flow data we have collected. In addition, and in the future, the insights uncovered here will serve as a foundational element for the demand of charging station near the I-210 corridor that our study has focused on. Now, I will pass the floor to Ethan, in which he will explain the implication of this data in the results and analysis section.
Thank you, Jaewon. Now let's explore the result and decipher their significance. Here we have a bar chart that compares the actual traffic flow against the predicted traffic flow for 6 different models. The weighted mean absolute percent error, or WMAP, is provided for each model, which is a measure of prediction accuracy. The stack model, which combines numerical and time series data, emerges as the champion model with the lowest WMAP of 10.16%, indicating the highest accuracy among the models evaluated. Moving forward, we have a line chart that visualizes the actual traffic flow captured by one of the vehicle detection system over a week. This graph presents a direct comparison between the actual traffic flow and the predictions made by our champion model. The blue line is the actual recorded data, while the green line represents the model's predictions. Note the close alignment between the two, which reaffirms the model's accuracy as indicated by the WMAP score. In this chart, we highlight the morning commute hours, 6 to 9 a.m., lunch break hours, 11:30 a.m. to 1 p.m., and the evening commute hours, 4 to 7 p.m. All these periods accurately showcase the traffic volume trends, demonstrating our model's ability to predict peak flows effectively. Another method we use to visualize our data consists of a heat map, simplifying the understanding of traffic flow and patterns over a 24-hour period. By utilizing data from all vehicle detection systems, we can observe the fluctuations in traffic throughout the days. The heat map's gradation indicates the intensity of the traffic at different times, with green showing low traffic and red indicating peak flow. Additionally, the maps for specific times, 5 a.m., 12 p.m., and 5 p.m., provides a snapshot of actual traffic conditions, highlighting the effectiveness of our visualization approach in capturing the full spectrum of daily traffic dynamics. Building on this method, we also applied the heat map technique to visualize predicted traffic flow. This table represents the estimated number of electric vehicles exiting the highway that requires charging based on the actual and predicted values that we have acquired into equation 3, previously explained by Jay. The differentiation in the color intensity along the exit path reflects the volume of EV exiting to charge, crucial for assessing the demand for charging station in proximity to these exits. Based on this, we compare the actual traffic flow with the predicted traffic flow heat maps for the same date. The predicted models closely mirrors the actual data with a few discrepancies in peak traffic flow times. This indicates our predictive algorithm's accuracy in forecasting traffic patterns. The maps on the right demonstrates the predicted traffic at 5 a.m., 12 p.m., and 5 p.m. Despite minor differences in the midday predictions, our model effectively forecasts higher traffic volumes during midday and evening periods. Now, let's take a look at the timeless of actual and predicted traffic flow patterns over a week. In this detailed visualization, the upper segment of the I-210 map is illustrated with the actual traffic data, with the lower segment reflects our predictive modeling for the same area. Each charging station is distinctly color-coded, representing its relative distance to the nearest highway exit, enhancing the clarity of the spatial relationship between infrastructure and road usage. This careful color differentiation enables us to discern the traffic flow patterns, both observed and forecasted with precision. Furthermore, the exit paths are shaded to correlate with the estimated volume of electric vehicles expected to depart highway in search of charging services calculated in the previous table. Facing the data and infrastructure scarcity challenge in the EV sector, we've successfully crafted a forecasting model leveraging traffic flow as a proxy for EV charging demand. Using a stack model with the WMAP of 10.16%, the model proves highly effective while our visual framework enhances understanding of our findings. Now, I'll hand it back to Wooky for future work.
As we look to the horizon, our journey doesn't end here. Our exploration into electric vehicle charging infrastructure is just the beginning. With traffic flow data as our compass, we've embarked on a quest to redefine how we predict and meet the demand for charging stations. In the near term, we aim to integrate real-time pricing mechanisms to boost the efficiency of EV charging networks. This strategy not only optimizes usage and balances the grid load, but also enhances sustainability. Our goal is to transform the charging experience into a wait-free, seamless interaction, significantly improving user satisfaction and convenience. Looking further ahead, the advent of comprehensive, granular public data will revolutionize our models. As the availability of detailed information on charging station usage becomes a reality, we will harness this data to redefine our predictions, making them even more accurate and actionable. Imagine a world where every charge is a breeze, where stations meet demand effortlessly, enriching our journey towards a sustainable, data-enlightened future. At ORSOL, we're not just envisioning this future, we're actively building it. Thank you.